Hello, and welcome back to the next lecture in this series about the church Turing thesis. Why are we talking about the church Turing thesis? What is it? Why are we talking about Turing machines at all? Well, we have Alan Turing to thank for that. But why was Turing motivated to build these machines, this mathematical model? And what did church do? They were working before we had electronic computers and long time before anybody was building programming languages that look anything like modern programming languages. So why were they motivated to essentially build programming languages? Let's try to set the stage for what they did by saying a little bit about the historical context. So David Hilbert was a famous mathematician in the early 20th century and before. And not only was he a famous mathematician, but he was also famous for being a famous mathematician. And when he suggested, here's a problem you might want to think about working on, well, a lot of people would sort of stop what they were doing and would work on that problem. And in a very influential lecture at the dawn of the 20th century, Gilbert set out a long list of problems, one of which was to find an algorithm for solving Diaphantine equations. If you don't know what a Diaphantine equation is, be patient, I will let you know. And then a while later, he posed another question, very algorithmic in nature. Find an algorithm to decide, given as input a first order logic statement, to figure out if it's valid. And there are variants on this to try to figure out if a formula or if a logic statement is true, let's say, for the natural numbers. So these are the questions that largely motivated the work of Church and Turing. And why don't I let you know a little bit more about these problems. This first one about solving Diaphantine equations is often known as Hilbert's 10th problem. And this problem about finding an algorithm is, since Hilbert was German, is called the Entscheidungsproblem, which just means the decision problem. It's an algorithm to decide. So there's a very close connection between these problems, actually. And Hilbert apparently never even contemplated the possibility that these algorithms would not exist. But Church and Turing were largely motivated by trying to show that, in fact, there cannot be an algorithm. And in order to do this, a major stumbling block was the fact that nobody had come up with a formal definition of what an algorithm is. I mean, mathematicians have been building algorithms for centuries, if not longer, but you know, they just knew an algorithm when they saw one. Nobody had ever tried to say, well, these are the only things that can be algorithms, and to try to even start formalizing what it might mean for there not to be an algorithm. And it's worth considering some of the intellectual obstacles that needed to be cleared before they could even do that. But first, let me remind you, or let me make good on a promise about what I need to tell you what a Diaphantine equation is. Let's start this with a simple example. Do there exist integers x, y, and z such that x cubed plus y cubed plus z cubed is equal to 33? The answer turns out to be yes, but this was not known until 2019. And in fact, the X, Y, and Z that have been found are huge. Let's say that the answer was no. Would there be a proof that the answer was no? In other words, could there be a proof of the statement for all X, for all Y, for all Z, X cubed plus Y cubed plus Z cubed is not equal to 33? Well, of course, since they do exist, there can't be a proof of that. But let's say that you had some other number, like 1098. Maybe X, Y, and Z exist. Maybe they don't. A Diaphantine equation, these are actually very simple examples of Diaphantine equations. They're just multivariate equations over with integer coefficients. So, if you have X, Y, and Z, then we might also have some terms, maybe plus X squared Y, or plus Y to the 90th, Z to the 10th. You can have all kinds of terms, just anything you can write down that looks like a polynomial with integer coefficients. So maybe to make sure what we're talking about with integer coefficients, maybe we'll also allow 57 X Z cubed. Okay. That's what a Diaphantine equation is. And much later than the work of Church and Turing, it was discovered, or it was proven after building on a lot of intuition that people had, that in fact there is not an algorithm for this, at least not if there's, let's say, 20 variables. And that also means that there are statements that look sort of like this, except with 20 variables, such that it's a true statement, but there will never be a proof of that statement. In other words, what's the connection between an algorithm to decide if a statement is valid, or it's easier to see about seeing if there's an algorithm to find out if there's a proof of a particular statement. If we're talking about a proof of something being true for the natural numbers, if there do exist X, Y, and Z, then there is a simple proof. You just give the numbers and do the arithmetic and see, yep, that comes out to just what it's supposed to be. And if there is not a solution, but there's a proof that there's not a solution, well, then here is an algorithm that could decide things. Just in parallel, you start trying all short tuples of variables and also the short proofs, seeing if you find a short proof of the fact that there is not a solution. And if you don't have any luck, then you start looking at longer proofs and longer solutions. And if everything that were true were provable, then since there either is a solution or there's not, you'd either find a solution or you'd find a proof that there's not, and that would give you an algorithm. And so the very fact that there is no algorithm for solving Diaphantine equations, which is a complicated thing to prove, and we will not be proving it, but the fact that there is no such algorithm also means that there are some true statements saying that some Diaphantine equation has no solution, but for which there will never be actually a proof of that. And that, of course, depends on what formal system you're using, but no matter what formal system you're using, if it looks like proving, a reasonable notion of proof, then there will be unprovable true statements there. Interestingly, even if there's just a single variable, there is an algorithm for solving univariate Diaphantine equations. It's wide open, apparently, if this is solvable when there are just two variables. So that's the historical context, some of the motivation for why it was interesting to people like Church and Turing to show that there was no algorithm. And I promised you that I'd tell you something about the intellectual obstacles that stood in the way of trying to formalize what an algorithm ought to be. Because intuitively, people knew what it ought to be. It ought to be something that's clear and unambiguous. It should give you an answer after a finite number of steps. And it better be something that you can write down, can be written down. But these three desiderata cause some problems, because if something can be written down, what does that mean? That means it's basically a bit string. And what is a bit string? But basically, it's an element of the natural numbers. You can represent numbers by bit strings, and any bit string can be interpreted as a number. So why is that an issue? Well, consider the following thing that looks like it ought to be an algorithm. On input I, which is just a natural number, but equivalently a bit string, interpret I as an algorithm and run I on some input. Well, let's just use the bit string I itself as an input. Why not? It's there, it's handy for us to use. And then after a finite number of steps, according to this rule, it should give us an answer. And if I of I is equal to 1, then output 0, else output 1. So this certainly looks like it ought to be an algorithm. It's clear and unambiguous, at least if your instructions are clear and unambiguous, then you ought to be able to take instructions and see if they are in fact instructions, and if they are, then follow them. And well, what's the problem? Well, this algorithm, if it outputs 1, outputs 0, so that's a contradiction, it can't possibly do that. But then if it doesn't output 0, then it outputs 1. You know, you're just stuck. So is this an algorithm? It can't be in your class of algorithms if you define something formally, because of this contradictory behavior. So that seems to sort of indicate that you can never really have a very satisfactory notion of a class of algorithms. And what Church and Turing essentially independently hit on was the infinite loop. Not because any of them were really interested in infinite loops, but because they had different approaches to modeling what seemed like computation to them, and what they came up with allowed certainly the possibility of infinite loops. So in other words, they threw out what seems like a pretty important idea that you'd want an algorithm to do, which is to give you an answer after a finite number of steps. And in fact, this is one reason why, in order to define what's decidable, we're really stuck using formalisms that give us infinite loops. That's why we talk about things like the Turing acceptable or RE sets, because if you stick with some computation notion that forces you to always halt, then you're going to leave out some things that are intuitively computable. So what kind of notions did Church and Turing hit on? Church essentially invented the lambda calculus. We're not going to be talking about lambda calculus, although certainly there are lots of places you can go to study about them. Turing hit on the Turing machine, which was motivated by just trying to see what somebody could do, a mathematician could do, if he was given clear instructions and a lot of paper and a really big desk and a lot of time. And fortunately for them, it turns out that, fortunately for all of us actually, it turns out that something is computable in lambda calculus if and only if it's computable by a Turing machine. And by computable, of course, here I really mean acceptable. The languages that are Turing acceptable are exactly the same class of languages that arise when you're studying Turing machines or when you're studying lambda calculus, or frankly, if you're studying any other model of computation like Java programs or C++ or anything else that you're likely to see as a programming language. And so this came to be known as the Church-Turing thesis, which is the belief that if you've got something that intuitively is computable, then you can write a program for it. And nobody who's inventing a new programming language, I believe, really thinks, okay, here's something that we can do with this programming language that was completely impossible before. Maybe they think it's more convenient in the new language, but nobody is really thinking that you can do something wildly new. And that's because they subscribe to the Church-Turing thesis. Now, why is this a thesis and not a theorem? It's because by definition, it can never be proved. It could only be disproved. If somebody comes along with a plausible notion of how something can be computed in the real world, which would allow us to do things that are not computable on Turing machines, well, then we will know that this was just a flawed belief. And there are people who come up with notions, ideas about taking a program and or a machine and bringing it extremely close to a black hole and hoping for certain nice effects from time dilation. And I think that these are never going to work. They need a huge amount of resources, and I just don't think the universe is going to allow something like that. I'm very skeptical about anything that involves infinity. Also, there are people who will claim, let me just highlight that this is controversial. People who take it as axiomatic that the human brain can, for instance, recognize that there are statements that are true that can have no proof. So certainly this takes us beyond the realm of what can be done with mechanical computers. And I find this extremely unconvincing. So if you take it as axiomatic that the human brain goes beyond the limits of computation on ordinary computers and programs, well, then it's an axiom. Of course you can believe it, but I see no evidence for it. And I see, in fact, a lot of evidence that the human brain is actually a pretty limited computer in many ways. So just to highlight the fact that this is not a theorem, we are, as a community, open to the idea that it can be disproved, but it's been around for a long time and it seems pretty well established. And even if somebody does come along with a convincing argument that says that you can do things that are not computable on Turing machines, well, this is still going to be a pretty important model of computation, things that you can do on ordinary computers with ordinary programs. And so it would still be well worth studying. There was something else I thought about mentioning, but let's move on. So we've got a notion of computation that is one that's served us well for well over half a century. Back when I was in grad school, which was less than half a century ago, it was also widely believed that things that you can do with ordinary computers also captured what you could do in a feasible amount of time. Now, with the advent of things like quantum computing, this is even more controversial, although it still arguably hasn't been demonstrated that quantum computers can do anything that involves yes/no questions that they can do significantly faster than deterministic machines, although certainly there's some evidence that maybe that should be true. We're not going to be getting into that, and certainly not in my lectures, and I don't think anywhere in this course, but it's just an example of how the assumptions that underlie our mathematics are open to change, and if some new models of computation come along, we are well equipped to study them, and we will do so. But in the meantime, there are a lot of reasons to be interested in what you can do with ordinary computers. And especially the focus of this series of lectures, what can't be done. So next time, we will be giving some examples of problems that are undecidable. So until next time, bye-bye.